Okay, so in this lecture we will talk about uh, some concepts which are very necessary. So we ended up in the last lecture on the B matrix formulation to derive strain values from the displacement values, and in this lecture we will try to address the stiffness matrix, and we will also see the concept of numerical integration. And the concept of numerical integration is going to be very important. You should practice calculating the shape functions using Lagrangian formulation for different types of element. You should take that as an assignment, or uh, it should be also discussed in the tutorials. So for instance, you can take, we have done it for this simple element for which we explained the concept. Now then you can do it for an element which has, let's say, 3 nodes in the bottom and only 2 nodes there. So for this one you can try with the Lagrangian formulation. You can try to find out the shape function n1, n2, n3, n4 and n5. So you should be in practice. Okay, so just a second. Okay, so I hope I have started. Yeah, okay, so let us now look at, so we established in the last lecture that strain can be calculated as B matrix into the displacement or the nodal values of the degrees of freedom. Okay, we will come back to this and discuss maybe a little bit of Jacobian also, but before we address Jacobian, we will look at the overall formulation of FEM. So now let us look at the energetics of the system. So let us say we have a body, and on this body we apply some surface forces in the form of traction. We apply some body forces, and then because of that there is some deformation on the system. This deformation can be reversible, so elastic, or can be irreversible, meaning plastic, or it can be combination of these two and various other types of deformation. But basically when you break down deformation, you only have two types, one which can recover back, another which cannot recover back. And then the rest of the things like creep deformation, plastic deformation, viscoplastic deformation, all things will lie somewhere in these two types, either reversible or irreversible. Okay, so we have done it, and now because of that, in a certain volume of this body, we have some amount of strain which has developed, and therefore the energy which we will have because of that strain will be this. So we are integrating over the volume omega, and this is the small amount of strain which has developed, delta epsilon. So we are taking transpose of that, delta epsilon transpose into stress, that term, and this term is called strain energy. Remember, it is a strain energy and not strain energy density, because strain energy density is per unit volume and we are multiplying it with the volume. Now we have, and why are we doing this, the transpose thing? You have to understand that we are not dealing in the 3x3 tensorial form. We are dealing in this kind of forms: epsilon 1 1, epsilon 2 2, epsilon 3 3, and epsilon 2 1, and stress also like that. Okay, so 1 cross 1 2 3 4 matrix cannot be multiplied by 1 cross 4 stress column matrix. Okay, so one of these you have to do the transpose of it, and this is why there is a transpose. Okay, and then we have the body forces which are also applied throughout the volume. So for that we have some amount of displacement which has occurred, and then we take the body forces. So instead of F, I can write F also, but F I will use in the end. So these are the body forces B, small b, integrated over the volume d omega, and then I have the surface traction, because of which I have the displacement, and that into the traction forces integrated over the boundary of the surface. Okay, so the surface is gamma. So these are the terms which I am going to have, and assume that the deformation is so small. So this is called the concept of virtual work. Okay, so we are imagining that there is some amount of strain and it should be zero. So whatever amount of force we are applying, that energy is consumed by or taken by the deformation, which is this part. So body forces we are applying, traction we are applying, and because of that the strain energy is consuming the energy which we are supplying to the system, right? So the net thing should be zero, because I don't have a source or sink of energy. There is no magnetism, there is no electric forces, so we are not considering those. If you have those, then you will have to keep on adding those things. Depending upon if it is a source or a sink, you have to take care of plus and minus and add all the terms which you will get because of magnetism, because of electricity, because of current, so all those things. Okay, so because we are talking about continuum mechanics, we are not dealing with magnetic electric forces, so we don't have those. We are in the macroscopic scale, so we don't deal with Coulombic forces, and we are not dealing obviously with the nuclear forces, so we are not in quantum field. We are in the Newtonian field, following the continuum mechanics concept. Okay, so we have this equation. All right, now because we are, so this equation has to be general. It is not that the body was initially at time is equal to 0 at rest, and then we applied some forces to it, and because of which the body got deformed a little bit and also moved a little bit, and this is my, so this is time. So let me write time in tau is equal to 0 and tau is equal to final time. But this equation will also be valid for an intermediate position. Okay, and in intermediate position I can have also, in initial state I can have some amount of strain which is already there in the material. So I can have some amount of thermal strain. Okay, and because of this strain, so we have to take care of the initial amount of strain, and for that we need to modify the equation a little bit. So we just have to add the term for the initial strain. So let me do that here. So I will have, because of that, I will have the first term, the volume integration, and this transpose of strain, and then because of that strain I will have some amount of stress, the initial stress which can be residual stress, thermal stress, and the final strain which I have is epsilon minus the initial strain which I had was epsilon naught, and then this whole thing integrated over the volume, and then I will have rest of the terms of body forces and surface forces, and that should be equal to 0. Okay, so this is what we have now. Okay, good. Now let us open it, let us expand this term. So we know that before doing this, we know that epsilon we can write as P matrix into the nodal value of the displacement or degrees of freedom. So in this case I can write del epsilon as B into U, which I had initially, and therefore I can, I should write it as B into del U, right? And therefore this del epsilon I can replace with this. So then my equation will be B del U, and so this will be B transpose del U transpose if I take transpose on both sides, right? So if I take transpose, this will change, so this will be del U transpose B transpose. So I will have del U transpose and then B transpose multiplied by sigma naught plus B transpose D into epsilon minus B transpose D into epsilon naught and d omega, and then I will have rest of the things equals 0, right? Okay, so I can actually take del U transpose out from the other two terms also. So let me write those. So I had volume integration of del U transpose body forces along the volume, and then I had a minus sign here, and I had traction forces on the displacement and d omega. So I can take this out from all these equations and I can only have the remaining terms, right? So this is going to be very easy to calculate because sigma naught you will know from the initial state. B matrix can be calculated, so that is not a problem. Actually there is no problem in calculation of any of the terms, but let us take the term which is coming because of the strain which is coming in the system in this increment where we are writing the equation, and that is this one, right? These are these are the terms which are coming because of the initial state of the body. So let us keep del U transpose out, and then we have B transpose D matrix, and epsilon we can write as B into U, and epsilon we can write as B into U, that we know, right? And d omega, and then I have other terms which will be, and this delta U transpose is out of everything, so then I have taken care of this term, so then I will have B transpose sigma naught, or I can simply write sigma naught minus d epsilon naught d omega minus integration of body forces. So del U transpose is already out, so body forces into d omega, and minus integration along the surface boundary traction forces into d surface equals 0. Okay, and now I can write it as, and so this term I can write as K matrix, this part, and K into U. Okay, K into U, and rest of the things I can write as the forces, because this is going to be a force which is coming because of the initial state. These are the body forces, these are the surface forces, all those equals 0. So you see, again we are coming back to the governing equation of finite element analysis, which is F is equal to KU, and here K, which is the stiffness matrix, is simply integration of over the volume B transpose D matrix into B d omega. Okay, so this is my K matrix, and how am I going to calculate this one? So if I have to and this integration is going to be over the element. If it is a quadratic element, it is going to be over this element. If it is a three-dimensional element, the volume, I have to do the volume integration. If I am dealing in 2 dimension, I have to do the surface integration. Okay, so I can change any integration. Which is being done over volume to an integration in the local coordinate system. So let us say I'm doing it for 2 dimensions, so I can do it as g zeta, and so integration over zeta and so I should write actually zeta eta d zeta d eta minus 1 plus 1, and then I have to write j d eta d zeta, and this is the Jacobian. Okay, so how I'm going there, how I'm getting this is actually very simple. So d omega I can write as integration of d omega, I can write as integration of dx dy, right, whatever is the limit a to b. And here also, so dx dy, now I have to change the dx and dy to the local coordinate system, and the relationship between local coordinate system and global coordinate system is given by the Jacobian, right? So what is the Jacobian? Jacobian is simply, if I have to derivate the shape functions with respect to local coordinate system, so I can write, let's say I can write it for 3 dimension, and now we are discussing Jacobian. Now we are discussing Jacobian. Okay, the name is Jacobian. The concept of stiffness is we have done it. The concept of a stiffness is here, the formulation, and then the question comes that how will we integrate this, and in order to answer that question, how do we integrate it, we are coming to the concept of Jacobian, and then we will go to the concept of numerical integration after this. Okay, so so if I have to write, and now I will write it for general situation, so for 3 dimension. So if I have, so in 3 dimension I will have, so in 2 dimension I had zeta and eta, and then in 3 dimension I will have another coordinate system which is psi. Okay, so if I have to write the partial derivative of shape functions with respect to the local coordinate system, del eta and del psi, so then I can break it down as del x by del zeta, del y by del del y by del zeta, del z by del zeta, del x by del eta, del y by del eta, del z by del eta, del x by del psi, del y by del psi. I am not able to write psi, so psi, and del z by del psi into del n by del x, del n by del y, and del n by del z. This is not very difficult. I have just written it in the matrix form, but if you write it, you will see that it is actually not very difficult, because del n by del epsilon will be simply this into that. So del x by del epsilon into del n by del x plus del y by del epsilon into del n by del y plus del z by del zeta. I have been calling it epsilon again, sorry. So del z by del zeta into del n by del z. So you see that this is just the chain rule of the differential. Okay, so if I have to find out the derivative of n with respect to zeta, I will open it up in x, y, z, right? And this will be the chain rule for the differential, and this is what I have written in this form. Okay, and when I write it in this form, then this term is whatever it is, del n by del zeta and del n by del eta, del n by del psi equals to, and this matrix, which is 3 by 3 here in 3 dimension, is the Jacobian matrix. So that is my Jacobian into del n by del x, del n by del y, and del n by del z. So you see the Jacobian is the relationship between the local coordinate, so partial derivative of the shape function with respect to local coordinate system, and partial derivative of the shape function with respect to global coordinate system. The relationship between them is given by the Jacobian, and this Jacobian matrix, which is simply del n by del zeta, so del x by del zeta, del y by del zeta, del z by del zeta, and del x by del eta, del x by del psi, and so on. This is my Jacobian matrix, and each coordinate x, y, and z I can write as summation of shape functions and the nodal coordinate values, right? So I can write as niyi and nici, right? So this Jacobian I can write as summation of del ni by, so x I can write as nixi, so del n by del epsilon into xi's, del ni by del zeta yi, del ni by del zeta zi, right, and so on, right? And so this I can again write as summation of del ni by del zeta and terms like that into xi, yi, ci. So actually I will have as many number of nodal values I have. So if I have 4 nodes, I will have x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. Okay, so I will have those terms. No. So if I have the nodal coordinates, then the coordinate I can write as n1 x1 plus n2 x2 if I have 2 nodes. Yeah, so I'm talking about one coordinate system. So if I have a 2-dimensional entity, even then, so okay, so if I have 2-dimensional element, for example, and I'm looking at x coordinate, so any value of x coordinate I can write as n1 x1 plus n2 x2, right? And so if I have to look at x coordinate here, then in a 3-dimensional element I will have also, in a 3-dimensional element, if I have to write the x coordinate between 2 nodes, then I will have x is equal to n1 x1 plus n2 x2, y will be n1 y1 plus n2 y2, and z will be n1 z1 plus n2 z2, right? And so I will have del n by del epsilon. So del n by del epsilon into xi I had, right? So I will have x1 and x2 and x3 only. I cannot have fourth row, and that is also true because these two has to be multiplicable, right? So these has to be multiplicable. So at each point, so I have del n by del zeta into x1, then del n by del zeta into y1. Y is ni yi. So del n, yeah, that is the problem. I have written it in a wrong way. So it should be x1, x2, x3, and here y1, y2, y3, and z1, z2, z3. Right? So del n1 by del epsilon into x1, del n1 by del epsilon, sorry, del zeta into y1, and del n1 into del epsilon into z1. Right? And then whatever amount of local coordinates I will have that many number of rows into that many columns I will have to multiply. So this is how, not this one, this is how I can write the Jacobian matrix. So, but basically this is Jacobian matrix, and if I have to simplify this, if I have to write simply, then I can simply write J, which is Jacobian, is equal to del xyz and del zeta eta psi. And from this you can remember always that this is the relationship between the partial derivative of the shape function with respect to the local coordinate system and the partial derivative of shape function with the global coordinate system. And if you find out the determinant of J, that is the volume of a small element which has the sides of d zeta, d eta, and d psi in 3 dimension. In 2 dimension, this will be just the area of d zeta and d eta. Okay, the determinant. Okay, so now let us look at our integration part. So this was our integration which we have to perform to find out the stiffness matrix. So we will write it again. So our stiffness matrix which we have to calculate is the volume integration over B transpose D matrix B matrix D omega. This will be in 3 dimension. In 2 dimension we will have to define either plane stress or plane strain condition, and in both condition we will have to tell that what is the thickness. You remember we did it in our lab courses that we always defined a value of thickness when we were solving the problem in 2 dimension. So if it is in 2 dimension, then the volume integration will be actually area integration B transpose D into B into thickness into, so D omega will become thickness into D area, and thickness value is constant, so there is nothing to bother about. B transpose D matrix into B matrix, and now this dA can be written as determinant of J, which is the area of the element, and that relates to the determinant of Jacobian into d zeta into d eta. So basically what I'm doing is I'm changing dx dy to determinant of j d zeta d eta. This is what I'm doing. If I have to find out the volume of a small element, then that in 3 dimension will be d zeta d eta d psi. Okay, so this is what I'm doing. So now I have to find out I have to do the integration of B matrix transpose D B matrix in a element along the local coordinate values of zeta going from -1 to +1 and eta going from -1 to +1. Okay, and then this, how that is related to global. See, the area is not going to change whether you do the integration in local coordinate system or global coordinate system. The values which are going to change is only because, so if let us say that this dimension is A and this dimension is B, okay, so when we are doing it in the local coordinate system, instead of having A and B, we are having always -1 and +1, and because of this, whatever difference comes can be taken care of by the determinant of J. Okay, so that is taken care of. So this is how we get this relationship, and now we can, now still we have not solved the problem of the numerical integration, but we have come from the global coordinate system to the local coordinate system, and so now our stiffness matrix can be written as -1 to +1, -1 to +1, B transpose D into B, D zeta, D eta. Okay, so this is what now we have to solve, right? And once we solve it, we can also do it for the other terms. So we can apply the same concept to the calculation of body forces into the volume integral was there. So this was the other term, and then we had surface integration. So surface integration was traction vector into d along the surface. So this again, you see we have d omega, and we can break it to d epsilon d zeta into thickness value and change the limits from -1 to +1, -1 to +1, and we can also do it for surface. Okay, so this scheme is applied in all the terms, but we are now focusing on only the first term, which is the stiffness matrix. Okay, all right. So now we have to find out the values. Now we have to find out a scheme which can do the integration. Okay, and now we will discuss the concept of numerical integration. I hope it can be done in this time period. Okay, so before we proceed to numerical integration scheme, if you remember, we spoke about the finding the area of a circle, which used to be a great deal for many people, and we discussed how it was done. So I told you in one of the lectures, probably in the first lecture, that the first in order to find out the area of the circle which has a radius of unity, so the area of that will be simply pi, right? And how do you find it? How do you find the value of pi? So the first guy, he made a square which was circumscribing the circle, and then you make a square which is inside the circle, completely fitting the circle inside. Okay, so inside the circle and outside the circle. So inside the circle, if you have a square, then the diagonal of that square, again it is going to automation. So diagonal of that square, which will be root 2a, will be equal to the diameter, which is 2r, right? And r is equal to 1, so you know what should be the value of a. So it should be 2a squared, sorry, we are making square both sides, so 2a is equal to 4 into r square. R is 1, so it is simply 4, so a is equal to 2, right? So the area of the inner square will be, am I doing it right? So the diagonal length will be root 2a. Root 2a will be equal to 2r, right? So 2a is equal to 4r squared. So a will be equal to 2 and the area of this square will be 4, right? Area of the inner square will be 4 and area of the outer squared. So outer square, the length of that, so the length of that square will be 2r, right? So the outer square A will be equal to 2r and r is 1, so it is simply equal to 2. So then the area of the outer square is also 4. So then there is a mistake. In both cases, how can it be same? So root 2 is the diagonal which is equal to 2r, and so the length cannot be equal to diagonal. There is something wrong. So a is equal to 2r. That is true. And a is equal to 2. So the same square is circumscribing and inscribing the circle. That is not conceivable. That is not conceivable. So r is equal to 1 and this becomes 2a. R is equal to 1. Okay, maybe it is a weird thing which is happening, but let us say r is equal to 2. Okay, so then root 2a will be equal to 2 into r, which is 2, right? So this is 4. Then square it on both sides, so 2a will be equal to 16, right? And then a will be equal to 8. This will be for the inner circle, and outer circle we will have a is equal to 2r, r is equal to 2, so here a will be equal to 4, right? 2 into 2 is 4. So here a is equal to 4 for outer. Now this is again weird. So it means that the square which is inside the circle is having higher length, so larger than the circle which is circumscribing this. Oh, this is weird. So let me draw a square first, and now there is no automation. So let me draw the square first. So this is the square, right? And if I make a circle inside, then the diameter of this circle is going to be equal to the side of it. So a is going to be equal to 2r. This is correct for outer circle, right? And for inner circle, what is going to be the truth? The diagonal is going to be equal to 2r, right? And diagonal is usually larger than the value of the length of the square. So there is some calculation mistake which I am doing, because I cannot get the length of the inner square to be bigger than outer square. So I am doing some mistake somewhere. Okay, but we have done it before. So let us look at the inner square. So let us look at the square which is inside, and the diagonal length is equal to 2r, right? Diagonal length is equal to 2r, and this is a square, so this side is a, this side is a, so that side will be simply square root of a square plus a square. So oh, that is the problem. I'm writing root 2a, it is actually a root 2 I should have written. Okay, so that is the problem. Okay, so now let us consider r is equal to 1. So for the inner square in the circle, the diagonal length is going to be 2r, which is simply 2. So a is going to be root 2. For the outer square, we will have length is equal to 2r and r is equal to 1, so a is going to be 2. So area of outer square will be 4 and area of inner square will be root 2 into root 2, so that will be 2. So the value of pi will be somewhere in between these two values, and it cannot be equal to this. So it should be somewhere between 2 and 4. And then people started, instead of making a square around a circle, they started dividing it into polygons. So instead of making a square, another guy made a hexagon, and then you find out the area of this hexagon and you circumscribe a hexagon outside, and then you define the range of pi by the area of the polygon inside and area of the polygon outside. And I have told you this, that one of the researcher did it for a polygon which had 128 number of sides, and did it for 9 years and found out the value of pi to certain decimal places. And then Newton comes and Newton does something. So the Pascal's triangle, if you look at Pascal's triangle, which we have discussed in FEM, so our Pascal's triangle, if you remember, was 1, then x and y, and then x square, xy, y square, and then x cube, and then x square y, then xy square, and y cube, and so on. This whole thing is, its Pascal's triangle is written, and it has been written in the ancient period also. So not talking about scientific period, but much before that. And how it comes is simply like this. So first term is 1 and then rest of the terms are 0. Okay, rest of the terms are 0, and the next term here will be summation of this and this. So 0 plus 1 will be 1, 0 plus 1 will be 1, rest of the things will remain 0. Then 1 plus 1 will be 2, right? And here you are getting 0 plus 0, 0, 0 plus 0, 0. So 0 plus 1 again becomes 1, 1 plus 0 becomes 1, right? And then you have, so you have 0 here, and you have 0 here, and 0, 0 is coming 0 like that, and 0 here, and 0 there. Okay, so 0 plus 1 comes 1, 2 plus 1 comes 3, 2 plus 1 becomes 3, and then 1 plus 0 becomes 1. Okay, so this is how Pascal's triangle moves. And if you and here I only explained actually the terms, but the coefficients are also important. Okay, So you see, if I just write the coefficient, I make this, right? And I can keep on making it. And this was known much before, and this is actually binomial theorem. So you can break any 1 plus x to the power n as long as n is an integer and it is positive. So it is a positive integer. And when you do it, you can keep on going and you can keep on making Pascal's triangle. And this triangle was known also in Sanskrit ancient books, and it was also in the other ancient civilizations. This has been found inscribed on stones and other things. So this is a very old thing, and well, you can go on and think if people knew about binomial theorem then or not. So our time is limited, so maybe I will stop at the end of this, which will lead to our Newton's Cotes quadrature, which is a scheme of doing numerical integration, so which is called Newton Cotes quadrature rule. And in the next lecture, maybe we'll talk about the real one, which is used in finite element analysis, which is called Gauss-Legendre quadrature rule, and we will talk about that in the next lecture. Okay, so and with this we will end our finite element elastic calculation. The thing will remain same for plastic calculation also, but we will probably move to plasticity and what plasticity is from our next lecture, how we take care of that in our modeling scheme. So 1 plus x to the power n can be broken using the binomial theorem as 1 plus nx plus n into n minus 1 divided by factorial 2 x squared plus n into n minus 1 into n minus 2 factorial 3 x cubed, and so on. Do you think this series is infinite? It is not infinite if n is a positive integer, and this is why you will get this Pascal's triangle, which is finite in size. You don't go to infinite numbers. And if you want to see the details on this, I will share a link of the video, and you can actually see what happens if you change it to fractions, what happens if you change it to negative powers, and the beauty of this Pascal's triangle relation with this. But this is binomial theorem, and it is not an infinite series because at somewhere you will hit n minus n, and because n is positive and it's an integer, so this will become 0. So you hit a 0 somewhere, and 0 multiplied by anything becomes 0 then, and so you don't have any terms beyond that. Okay, so this is a finite series. So you can start with 1 plus x when n is equal to 1. So this is basically 1 plus x. If you have 1 plus x squared, then it is 1 plus 2x plus x squared, and so on, right? 3x plus 3x squared plus x cubed. So this is what you get. And then, so before Newton, it was used only for positive integers, but Newton applied it for negative and fractional values. So he applied it for 1 plus x to the power minus n, and this simply becomes 1 by 1 plus x to the power n. And then he applied it for fractions also. So 1 plus x to the power 1 by 2, well, 1 by n in the general terms, and it will follow the same rule. So if you have to break it using, but the thing is, if you go to fractions and if you go to negative powers, then the series becomes infinite. So because negative, you never hit n minus 1 n, because n is negative, so it will never become 0. So you don't go to finite, you go to infinite series. And when you do it for fractions, then When you do it for fraction, then also you can break it as 1 plus. So in this case it will be nx, it will be 1 minus n into x plus 1 by n. So this is actually n. So nx into n minus 1 divided by factorial 2 x squared and so on. Okay, so you can break it down like that, and then he found that you can actually find out the square root. If n is equal to 2, then you can find out the square root of this, right? And using this, he calculated the formula for the area of the circle, and that detail also you will find out in the shared video link, and you will see how he calculated those. He calculated the value of pi, because you can write the equation of circle as 1 minus x squared, right? And then y is actually square root of 1 minus x squared. And if you have to find out the area, and here this is the equation of a circle where the radius is equal to 1 and it starts from the origin. So this is my circle, and the equation of the circle is simply this. And if I integrate y dx over 0 to 1, then I'm simply talking about this area, right? And that I can write it as y is equal to root over 1 minus x squared dx, right? And in order to find out this one, you simply had to replace x with minus x and n with 1 by 2 and open it in the binomial form and keep placing it. So then you have terms like, so this will be equal to integration of 1 minus x squared to the power 1 by 2 dx, right? And this you can expand as, so 1 minus x squared to the power half, that you can expand. So that will be 1 plus n is half and x is minus x squared, and then you have n into n minus 1, n into n minus 1 divided by factorial 2 x squared, and x is minus x squared, so minus x squared squared and so on. Okay, so these terms are actually not very difficult. So then you get 1 minus half x squared plus, so factorial 2 is basically 2, so minus half into half is minus 1 by 4, minus 1 by 4 divided by 2 is minus 1 by 8 into, so this will become positive, so this will be x to the power 4 and so on. So 1 minus half x squared minus x to the power 4 by 8 and so on, and then you simply integrate these from 0 to 1. So integration of this will be x, this will be half into x to the power 3 divided by 3 minus x to the power 5 divided by 5 into 8, 40 and so on, and you just have to plug the value of upper limit and lower limit and you will get the value of pi, right? Because the area will be simply pi by 4, because we are calculating the area of 1/4 of the circle, and this is how you get the value of pi without making a polygon inside the circle and polygon outside the circle. So this binomial expansion can be used as in order to do the numerical integration, and you got the sense of it here already. So you got the sense here, how are we going to do the numerical integration without actually performing integration. Yeah, without actually performing integration we will do it. Here still we are doing the integration, but we will use this concept to go to Newton's quadrature formulation in the next lecture. Okay, so